Hello, Hornets, and welcome. Today we're going to be going over 4 problems using the limit comparison test and the direct comparison test. This is a follow-up to the notes that I've already given on the 2 rules. So in front of you, you'll notice I have a direct comparison test that I'm going to be doing. Now, the first thing I want to do is select a series that I already know is either smaller or larger than what I have. Now, I can already see that this is similar to a geometric series where the ratio is 3/7. That's what I'm going to use. Since I know that the summation as n starts from 1 to infinity for 3/7 to the n will converge because it's a geometric series where the common ratio is less than 1, I'm going to now compare them. Since I know that every single term in the series that I'm working with is going to have a larger denominator. A larger denominator automatically implies that I have a smaller series. So we can definitely say that the series 3 over 7 to the n is larger than the series 3 over n, 7n plus 3. And because we have a larger series that converges, it forces the smaller series to converge. This is by the direct comparison test, and that's what I now need to write. So since the summation of 3 to the nth power over 7 to the nth plus 3 is 7 to the n. There we go. Is larger than the series that I'm considering. This is the hardest part, is writing all of this little stuff down. 7n plus 3. And the series n equals 1 to infinity of 3 over 7 to the nth is a converging geometric series. Where r absolute value is less than 1 by the direct comparison test, the series n starting at 1 to infinity of 3 to the nth over 7 to the nth plus 3 must converge. And there we have our statement. Since the summation from 3 to the nth over 7 to the nth is greater than the summation we're considering, and this is for all values of n greater than or equal to 1. Now let's put that in. For all n greater than or equal to 1, let's just try to be as specific. And the series 3 over 7, 3/7 to the n is a converging geometric series where the ratio is less than 1. By the direct comparison test, the series must converge. We're done. That is my first example. Let's take a look at another for direct comparison test. Now, you'll notice in this direct comparison test, we have that plus 6. That's what I'm not going to look at. That plus 6 is creating a larger denominator. That larger denominator is creating a smaller series. So what do I know? Well, if I look at the series and I get rid of that 6, I'm looking at n to the 5/2 power, which is a p-series. And that p-series is what I'm going to use to test. Because I know that this p-series having a p greater than 1 must be convergent. So I'm looking at a convergent p-series, and I already know that the series is larger than the one that I am considering because the denominators are larger than the other, I can immediately go to the direct comparison test. Since the summation of 1 over n to the 5/2 power is greater than the summation, and you'll notice I'm just writing my statements all over again. 1 over the square root of n to the 5th plus 6. Let's just put in for all n greater than or equal to 1. And the summation from n starting at 1 to infinity of 1 over n to the 5/2 power is a converging p-series, okay, by, make sure you can see what I'm writing, by the direct comparison test, the series summation n starting 1 to infinity of 1 over the square root of n to the 5th plus 6 must converge. We're done. Alrighty. Let's go ahead and take a look at another example. This time, we're going to be looking at the limit comparison test next. And I've got an interesting problem to show you here. So here we have our limit comparison test. Now, you'll notice the net p that we're going to work with ignores the exponential, ignores the coefficient, and ignores the constant at the end. So we're only looking at n over n cubed. The numerator is going to have to stay 2 to the nth. So we want to look at, or use, we will use the summation of 2 to the nth over n squared, as n starts at 2 and goes to infinity. So this is what we're going to use as our comparison. So let's go ahead and get started. That means that I'm going to make the limit as n approaches infinity for the series that I have, n 2 to the nth over 4n cubed plus 1 divided by the series that I'm working with, 2 to the nth over n squared, and I'm going to simplify that. Now the simplification is basic algebra, so we're going to bring this up as a reciprocal. This is going to let me have n 2 to the nth multiplied by n squared, and I'm looking at 4n cubed plus 1, and I'm multiplying it by 2 to the nth. Now you can clearly see the 2 to the nths are going to cancel, and n squared times n gives me n cubed. And I'm now looking at something that I can work with. N cubed divided by 4n cubed plus 1. The n squared, 2 to the nths cancel. And this is 1/4 a positive finite value. Now, since I got a positive finite value, I can now make my conclusion. Therefore, make sure you can see it. Therefore, the series summation n starting at 2 and going to infinity of n 2 to the nth over 4n cubed plus 1 diverges by the limit comparison test. When compared to the divergent series summation, n starts at 2 and goes to infinity, of 2 to the nth over n squared, period. Now, some of you are saying, hey, wait a minute, how did we know that that series converges or diverges? Well, I will point out that this diverges by Feppel, and we can clearly see that this will diverge. It has a faster function in the numerator and therefore has no choice. So this is a converging series, a diverging series, let's write it down, by Feppel. And there we go. That is my first example for the limit comparison test. Let's take a look at another one, please. This is my last example and the last for this video. Step one, we have to start by asking ourselves, what are we working with? And you'll notice I'm going to ignore the 4's, and I'm only looking at the square root of n squared. The square root of n squared is 1 over n. So that's what I'm going to work with. We will use 1 over n. And you'll notice 1 over n is a harmonic diverging series when we put it as a series from n starting at 1 to infinity. So please just be aware of that. If I'm using this, I'm now going to want to construct my limit. The limit as n approaches infinity, and I'm going to put 1 over the square root of 4n squared plus 4. But please be patient here, because if I just use 1 over n, I'm going to get n over the square root of 4n squared plus 4, which means that I'm either going to want to talk about it in terms of 1 over the square root of n squared, or perhaps do a little extra work. I personally like this. Why? Because if I have this, I can now simplify it, and I can now make this the square root of n squared over 4n squared plus 4 square root, which means that I'm looking at the limit as n approaches infinity for n squared over 4n squared plus 4 to the 1/2 power. And according to my rules of limits, I can do the limit first and then take my power. So that's what I'm going to do. Now, I can clearly see that my limit is 1/4. So I'm looking at 1/4 to the 1/2 power is 1/2, a positive finite value. Now I can write my statement. Therefore, the series as n starts at 1 and goes to infinity for 1 over the square root of 4n squared plus 4. And I'm now going to say diverges by the limit comparison test, LCT, when compared to the series, to the divergent series summation, n starts at 1 to infinity of 1 over n, period. Let's now make sure you see my statement. So here it is. We found we had 1/2, a positive finite series, and therefore the series that we're looking at must diverge by the limit comparison test when compared to the divergent series 1 over n. That's the limit comparison test and the direct comparison test in action. We will be working with this over the next few days, next week. or as we get through this. So please hang in there, keep practicing, and keep trying to do it, all right? You will get better. Have faith. Thank you very much. Be well and be safe and take care. And remember, it's easy to be mean, so be nice to each other. Change starts from within. Bye-bye, Hornets.